Hi everyone, myself Srivalli, working as an assistant professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today, the area of presentation includes equivalence classes. So let us discuss in detail. So what is meant by equivalence classes? So in the previous session, we have discussed about what is equivalence relation and how to solve the problems on equivalence relation. So the equivalence relation, if you recall that equivalence relation, so the relation which satisfies a reflexive property and symmetric property and transitive property. So the relation which satisfies reflexive, symmetric and transitive properties are called, it is called equivalence relation. So now based on the equivalence relation, we are going to discuss the next concept, that is equivalence classes. So here, let us understand what is meant by equivalence classes now. Suppose capital A is a set and capital R is an equivalence relation. So here let us suppose we are considering one set which is denoted with capital A and capital R, which is nothing but this is an equivalence relation. Means here we already proving that this capital R is already equivalence relation. So that means in the previous class we have discussed how to find out the particular given relation is called an equivalence relation. So here an equivalence relation which satisfies reflexive, symmetric and transitive, we can say that it is called equivalence relation. Now we are saying that this R is already proved that it is an equivalence relation. Now this is an equivalence relation on which set here? It is capital A. For each element x in A, the equivalence class of x is denoted by within the square bracket x. Means here, for example, I am going to consider set A is equal to 1, 2. So this is set A. Now, let us suppose relation R is equal to here 1, 1 and 2, 2. So here, and also I am going to write here 1, 2 and 2, 1. So this is a relation that I have. Now, here what the thing is, to find out the equivalence classes, first you need to find out whether that R is an equivalence relation or not. So if you observe here, set A is equal to 1, 2 and R is equal to 1, 1, 2, 2 and 1, 2, 2, 1. So here, so let us understand whether this is an equivalence relation or not. So 1, 1, 2, 2, this is reflexive property. Why? Because here for all A belongs to capital A, there is A belongs to A in the R. That's why this is called reflexive. And whether, let us prove that whether it is symmetric or not. Symmetric means for every A comma B belongs to R, there should be B belongs to A. That is nothing but 1, 2 is there and 2, 1 is there. So this is called symmetric property also. Now let us see whether this is a transitive relation or not. So here 1, 1 is there. And the order page starting with 1, it is there. 1, 1, 1, 2 is 1, 2. So here we have 1, 2. And here 2, 2, 2, 1, we have 2, 1. Which is nothing but this is also satisfying transitive property. Then we can say that this is called a transitive relation. So as these all the three properties we are getting satisfied, we can say that capital R is called an equivalence relation. So this is capital A and this is R. And this capital R is an equivalence relation on which set here? This capital A. Now, how to find out the equivalence classes? For each element x in A, means here the elements whichever are present in capital A, I am just denoting with here x. So for each element x in A, means each element I am denoting with x in A, and the equivalence class, how you will denote is within the square bracket x. So for each element x in A, the equivalence class of x is denoted by within the square bracket x, and the set of all elements y in A which are related to an element x of A is called the equivalence class of x. Means the set of all elements y in A, means if I am denoting this first element 1 as x, the other elements whichever are present, how many are present, those elements I can consider it as, I can denote with as small y. Now, which are related to an element x of A, means if this x element, like with any element of y, if it is relating, then we can say that x is related to y. And we can say that equivalence class of x, we can write it as those two elements in that. So here, the equivalence class of x, mod of x or square bracket x is equal to y such that y belongs to A. For example, here the first element I am going to consider it as x. The second element or third element, how many elements you are having, those all elements will denote with small y. Now y such that y belongs to a. Yes, this y element is also belonging to capital A. X comma y should belongs to R. Means these two elements together as an ordered pair should belongs to capital R. Then we can say that equivalence class of x is equal to, so if this 1 is related to 2 in the relation, then we can write that 1 comma 2. So this is equivalence class of x. So the equivalence of class with respect to R means with respect to this R equivalence relation we are finding out. That's why we are representing equivalence class of x with respect to R. Means here in the suffix you will be writing R. So this is like how we need to find out the equivalence classes. So here let us see few examples so that we can understand how to find out the equivalence classes. So here let A is equal to 1, 2, 3, 4 and R is equal to 1, 2, 2, 1, 1, 1 and 2, 2, 3, 3 and 4, 4 also. So this is R and this is an equivalence relation. Means in the question itself we are mentioning that this is an equivalence relation, means it is already proved that capital R is an equivalence relation. That is nothing but which satisfies reflexive, symmetric and transitive property. Now determine the equivalence classes. So here let us check. So no need to check actually this R is an equivalence relation or not, as it is already mentioned in the question that it is an equivalence relation. But for your understanding purpose, just understand what how R is an equivalence relation. Now here to satisfy this R equivalence relation, as we know that we need to satisfy a reflexive, symmetric and transitive. Let us go for the reflexive here. So to become the reflexive property, it should satisfy, it should have in the relation that 1, 1, 2, 2, 3, 3 and 4, 4. So let us check here. 1, 1 is there, 2, 2 is also there, 3, 3 and 4, 4. So as all the A elements which are present in set A as in the form of A comma A belongs to capital R, then we can say that it is satisfying reflexive property. In the same way here, AB if it is there, B comma A also should exist in the relation to become the symmetric relation. So 1, 2 is there, 2, 1 is there and here and we don't have any A comma B elements. So we cannot check B comma A element. So by default it is satisfying symmetric property, as this is there here, as A comma B are there, B comma A is also existing in the relation. Next let us go for symmetric property. So transitive property here. So next one is transitive. How to find out the transitive is, so here if AB is there and B comma C is also there, then A comma C also should exist in the relation. So that is nothing but 1, 2, 2, 1. Next 1, 1 also should exist in the relation as it is there here. So in the same way here, 1, 2, 2, 2, 1, 2 is there. So starting with 2 we don't have. Next 2, 2, 1 and 1, 1, 2, 1 it is there. 2, 1 and 1, 2. So 2, 2 it is there. So like this if you check here, this is satisfying transitive property also, as these all the three properties are satisfying. That's why this R is called an equivalence relation. Now this set A and this is an R is an equivalence relation. Now determine the equivalence classes here. So we have already solved the solution here. So how many equivalence classes we will be getting here? So altogether we'll get here the number of elements in the set A. It belongs to, means it depends upon the number of elements in set A. So here as we have 4 elements in set A, means 4 equivalence classes with respect to R we will be getting. So here equivalence class of 1, equivalence class of 2, equivalence class of 3 and equivalence class of 4. Now 1. Now we need to check in the relation, is 1 is related to any other element in the relation or not. So if you observe, 1 is related to 2 and 1 is related to only 1 and it is not related to 3 and 4, as we don't have 1 comma 3 and 1 comma 4. So as we have only 1 comma 2 and 1 comma 1, we can say that 1 is related to only 2 element but not with any other element. Then we can write in the equivalence class here 1 comma 2. So in the same way 2. So as 1 is related to 2, which is nothing but it is vice versa. 2 is also related to 1 but not with any other element as it is showing here. So here also we'll get equivalence class of 2 is 1 comma 2. Next 3. So if you observe in the relation, 3 is related to only 3 but not with any other element. So we'll get 3 here. And 4, if you observe equivalence class of 4, 4 is also related to only 4 but not with any other element. So we'll write here only 4. So these are the equivalence classes of the set A, that is equivalence class of X. So it is nothing but 1, 2, 3, 4. For example, along with the order pairs, this order pair means along with this relation, for example, if I write 2, 3, so can I find out the equivalence class? So here I cannot find out the equivalence class. Why? Because to find out the equivalence classes, first it must be an equivalence relation. But this is not an equivalence relation here. Why? Because even though it is satisfying here, reflexive property, but it is not satisfying the symmetric property. So why? Because, so if 2, 3 is there, means as per the symmetric rule, so if A, B is existing in the relation, B, A also should exist in the relation, then only we can say that this is called symmetric property. But here we have 2, 3, but we don't have 3, 2. So that's why it is not an equivalence relation and we cannot able to find out the equivalence classes. But if I write along with 2, 3 and 3, 2, this is a symmetric relation. But let us check whether it is a transitive property or not here. So 1, 2 and 2, 3. 1, 3 should be there, but we don't have 1, 3 here. Even though it is not a transitive property here. Why? Because as we don't have 1, 3. So 1, 2, 2, 1, A, B, B, C, AC also should be there. So here 1, 2, 2, 1 is 1, 1, okay. So 1, 2, 2, 3, 1, 3 should exist. So I don't have. So just make it as 1, 3. So if I make it as 1, 3 here, then it is a transitive property. But it is not a symmetric property here. Why? Because if 1, 3 is there, 3, 1 also should be there. So if I add 3, 1 here, so again check transitive property, this is symmetric property here. So now 1, 2, so 1, 2, 2, 1, 1, 1 and 1, 2, 2, 2, 1, 2 we got, and 1, 2, 2, 3, 1, 3 it is also existing here. Now 1, 1, 1, 2 it is there. So 2, 2, 2, 3, 2, 3 should be there. Yes, 2, 3 is also there. So in the same way here, if you observe 3, 2, so 3, 2, 2, 1, 3, 1. So 3, 1 is existing here. So and 3, 2, 2, 2, 3, 2 is there. 3, 2, 2, 1, 3, 2, 2, 3, 3, 3 is there. So 3, 3 is also existing in the relation. Now if you go for 1, 3, so 1, 3, 3, 1, 1, 1. That is also there. 3, 1, 1, 2, 3, 2 should be there. That is also there. So now if we add the order pairs 3, 2, 1, 3, 3, 1 and 2, 3, then it is an equivalence relation. Now if this is an equivalence relation, now how to find out the equivalence classes here? So as usual, the equivalence classes will be based upon set A, that is like you will get 1, 2, 3, 4 with respect to R. For this particular equivalence relation I am saying here, just this is an example. So here equivalence class of 1. So as 1, so if you observe 1 is related to 2 and is also is related to 3, that's why we can write it here 1, 2, 3. As 1 is related to 3 also. Now 2 is related to 1, is also related to 2 and this is also related to 3 here. So you can write 1, 2, 3. And now if you observe 3, so 3 is related to 1, 2 and even 3 also. So 3 is related to 2 and it is also related to 1. So 3 is related to 3 also. Then we'll get 1, 2, 3. And 4 is related to only 4 but not with any other element which are present in the set A. Then we'll get only 4. So these are the equivalence classes if we add these order pairs along with this given equivalence relation. So this is like how we need to find out the equivalence classes. So next let us see the another example. What are the equivalence classes associated with each of the following equivalence relation on 0, 2, 4? And here we have two questions. So these are nothing but relations R. And this is also R. And the given whichever it is called, it is set A. We have to consider it as set A. So here set A is equal to 0, 2, 4 and R is equal to 0, 0, 2, 2, 4, 4, 0, 2, 2, 0. and they are saying that find out the equivalence classes. So here, how many equivalence classes we will get is here based upon the number of elements in the set A. So here we have 3 elements, we'll get all the 3 equivalence classes for 0, 2 and 4. This is with respect to R. Now how to find out the equivalence classes? And they said that these are equivalence relations. These are already proved that this is an equivalence relation. So 0, 0, 2, 2, 4, 4. Yes, reflexive. Symmetric 0, 2, 2, 0. Transitive 0, 0, 0, 2, 0, 2. 2, 2, 2, 0, 2, 0. It is there. So this is already proved that this is an equivalence relation also. Why? Because reflexive, symmetric and transitive properties are satisfying here. Now, equivalence class of 0. Now, how to find out this equivalence class of 0? So, 0 is related with 0 and 0 is also related with 2. Then I can write here 0, comma 2. Now, in the same way, 2. 2 is related to 0 and it is also related to 2. You can write 0, comma 2. Now, 4. 4 is related to only 4 but not with any other element. So, these are the equivalence classes here. Now, next one. Next relation on the same set but different relation here. This is an equivalence relation only. You need to find out the equivalence classes. Now, here again same thing, equivalence class of 0, 2, 4 you will get. So, 0 is related to only 0 here and it is not related with any other element in the set. And in the same way, similarly, 2 is also related to only 2 and here 4 is also related to only 4. So, these are the equivalence classes for this particular given equivalence relation. So, like this, we need to find out the equivalence classes based on the set A and equivalence relation. So, what we have discussed today in our classes. So, first we have discussed what is an equivalence class, how to find out the equivalence classes, how to represent the equivalence class. So, based on the equivalence relation, we can able to find out the equivalence class. Next, we have partition set. So, this is all about our session, today's session. So, thank you.